Hello and welcome to part 2 of lecture 11. So in this part, we're going to actually introduce matrices into our discussion of linear algebra. So it's kind of interesting. We're almost at the end of week 3 here, and we haven't really talked about matrices. So I do want to point out that matrices kind of arise naturally when we study linear maps. So I'm going to kind of build upon your knowledge of matrices from Math 1B03, and kind of, some of this I'll kind of run through quickly because I assume that you know this material quite well. So remember that when I write A is an M by N matrix, what I mean is that there are M rows in my matrix and N columns. As well, I write A sub ij to mean the entry in row I and column j. Sometimes we'll see this, we'll write A dot J or AI dot, and this means either all entries in column J, or maybe we want to pull out all the entries in row I. So that's what the second notation means. Okay, with this notation under our belt, what we'll do here is come to an important theorem, or definition, excuse me, which it takes any linear map between finite dimensional vector spaces, V and W. And so V will have a basis V1 up to Vn, and maybe let me clean this up so we're very clear about what this space is. This is Vn. So we have a basis for V and a basis W1 to Wm for the vector space W. Now the matrix of T with respect to these bases is the M by N matrix, right? And I have this in the right order. M, which is the dimension of W, and N, which is the dimension of V, where, oh, I should give it a name here, is the matrix MT, where entry Aij satisfies the following property. So Aij is a coefficient that shows up when you look at what taking the jth basis element of your vector space V, plugging it into T, so you get an element in W, and you express it in terms of the basis for W. So here we have A1J W1 plus A2J W2 all the way up to Aij Wi, and keep on going all the way to AMJ WM. Right? So remember, each of these red things here is my basis for W, and each of these guys here, these are elements in my field F. So the entry that goes in spot ij is take T and my basis element Vj, stick it into the function, write it in terms of the basis, and look for the coefficient of Wi. So I'm going to give you a picture to kind of hopefully help you kind of keep track of this information, because there's a lot of things floating around here. So just remember our setup, maybe I'll put it up here as part of our setup, is we're looking at T. It's a linear map from V to W, and we're also given that V has a basis, V1 through Vn, and we're given a basis for W, W1 up to Wm. So we need to use all of this information. So each of these basis elements, they live in V, so we can apply the linear map to it, and we get something in W. Because we get something in W, this guy is an element in W, we can express it uniquely in terms of our basis, right? So we can write this as A11 W1 plus A21 W2, and so on, right? So we get A1 WM, and now we have A21 W1, A22 W2, all the way out to AM2. Sorry, I did that wrong. I got my indexes mixed up. See, M1, oh no, that's right, WM, and I go all the way down, so I get AN1W1 up to AMNWN. Okay, so what am I going to do with this information? Okay, so somehow I need to create an m by n matrix from all of this information. And here's kind of what we're going to do. You want to think of labeling the columns with the basis elements of V, and you want to label the rows with the basis elements of W, okay, where you're going to. So you're starting from the V's and you're going to the W's, and now TV1 gets sent to this particular element right here. So if we know our basis, if we know each row is corresponding to a particular basis element, all we need to keep track of are the coefficients. So in the first column, I'm going to put A11, A21, all the way down to AM1. So you can think of this as V1 gets sent to A11 times W1 plus A21 times W2 plus all the way down. So I'm keeping track of all the coefficients. Now V2, where does it get sent? Well, the important pieces of information are right here, A21, A22, all the way down to AM2. And we fill in the rest of the matrix in a similar fashion. Okay, so this gives us our standard matrix associated to T with respect to our bases V1 and W1. So one thing you'll notice is that once you pick the V and the W, you get a matrix. But if I change my basis as V and I change my base as W, I'm going to get different matrices. So one theme in the course that we're going to see is picking good bases for the V's and the W's so that this matrix that I've just written here has a particularly nice form. So that's one thing to kind of keep in mind. But we're going to come back to this over and over and over in this course. So hopefully this example, this kind of picture helps about what you're doing. And let me highlight here again, what we've done here is that the column K contains the coefficients of TVK, which we're coming from up here. And I just want to tie this up to what we saw in Math 1B03, because we actually did a very special case of this in 1B03, and it was this special case here. So in 1B03, we did a lot of cases where our vector space was Rn, and our other vector space was Rm, and we use usually the standard basis for Rn and Rm. And if you took any linear map, then what was called the standard matrix of our map was the matrix that you got where in the first column, you would take E1, your first standard basis vector, map it over to Rm, and you got a vector, and that formed your first column. Then you took the second basis element, that gave you your second column, and you did this all the way down, and that gave you all of your columns. So this was called the standard matrix. So if you're a little rusty on all of this, I would say go back to your Math 1B03 book and look at this construction, this result, and just understand what we're doing in this definition is we're generalizing this to any vector space and any linear map. So in the next part, I'll spend some more time doing a couple of examples so we get used to this idea. See you in the next part.